Hello all. After kind of a long detour we took by going over Edexcel material from the UK, and I also went over an international GSE test that was paper 1, I believe, or maybe it was paper 2, I don't remember. So anyway, we are returning back to the regular units 1 through 6 of the international Edexcel curriculum. And in particular, this is, I believe, the most recent Unit 5 test from January 2026, okay? And as I said in previous videos, for some reason lately, and I'm talking about this past paper season, like in January 2026, and in November 2025, they put out two tests, a Unit 5 and a Unit 5A. And from what I checked, Unit 5A is different from this test we are taking now. So at some point, I hopefully will find time to go over it. But anyway, let's dive into this test now, okay? The usual things, section A, 10 multiple choice questions, 1 mark each. It should take you about a minute for each question. And then section B are long writing problems and algebraic problems and stuff like that. Those should take about as many minutes as the marks they award. So if it awards 15 marks, it should take you 15 minutes and something like that. And if it's a writing problem in which you have to write statements for or against something that they ask you, if it awards 5 marks, you should provide 5 statements and so on. Anyway, question 1. A student investigated the absorption of gamma radiation. He measured the background radiation. Which of the following should he do to correct the count rate for the gamma radiation? So the count rate, okay, so that's important. So the first two options talk about the background count. So those are immediately wrong. And then option C says add the background count rate. That doesn't make any sense. So we have to subtract the background count rate. So option D. Okay. So what this means is that let's say you have a source and a counter that receives the radiation from the source. Then the counter also receives the radiation from the atmosphere, from the background. So you have to subtract that pretty much there. And count rate means becquerels. So becquerel is 1 count per second. Okay. Question 2. Earthquakes can cause buildings to oscillate. The effects can be reduced by damping the oscillations using ductile materials. Which of the following describes a ductile material? It behaves elastically under compression. No. B, it can undergo significant plastic deformation. This is it. This is the definition of a ductile material. Okay. It withstands a large stress before breaking. That can be brittle as well. So no. And D, it has a large Young modulus. No. Okay. And again, I remind you that if you have the stress strain curve of this material, the ductile material, it will look something like this. And this will be the large plastic deformation region. Okay. Question 3. Which of the following is a unit for intensity? Intensity is measured, is calculated using the power output of some radiation over 4 pi r squared for the surface area of a sphere on which that radiation is distributed, or for stars, L, the luminosity over 4 pi r squared. So you immediately see that the units are watts from the luminosity and meter squared for the r squared, so A. Okay. 4. The distances to nearby stars can be determined using trigonometric parallax. Star X has twice the parallax angle of star Y. Which of the following statements is correct? So let's draw the situation actually. So if this is the sun and this is the Earth, okay, this is 1 AU, 1 astronomical unit, and so is this distance. And let's say there is a star, we want to measure the parallax. So the parallax angle is this one, okay, that's theta. So this is star Y. If the star is has twice the parallax angle, it will be 1/2 of the distance away, right? So that will be now 2 theta, and this will be star y, x, I'm sorry. Okay, now let's go answer. The distance to x is 4 times the distance to y. No, the distance to x is 2 times the distance to y. That's also wrong. The distance to x is 1/2 the times the distance to y, which is what we see in this scheme here, right? So option C. I don't know why my screen does that crazy motion. I think it's because I touch it. But if you know how to fix it, let me know in the comments. Okay, 5. The ultimate fate of the universe is uncertain. Which of the following is true for an open universe? Option A, the average density of the universe is equal to the critical density of the universe. That will make for a flat universe. B, the average density of the universe is less than the critical density of the universe, which is the case, right? Because then the gravitational attraction will never be able to counteract the outwards expansion, so it will keep expanding forever, which is what open universe means. C, the mass of the universe is equal to the critical mass of the universe. No. D, the mass of the universe is greater than the critical mass of the universe. No. Okay, 6. Which of the following describes the spontaneous nature of radioactive decay? The decay is a natural process. No. B, the decay is a random process. So random means, when we say random, we mean we cannot predict when the next decay will happen. Okay, so it's not. So even though it sounds correct, it's not correct. So C, we cannot influence when the next decay will occur. That's the answer. Okay. D, we cannot predict when the next decay will occur. So no. Okay. Shall I write it down? So spontaneous. Oops. Spontaneous means the decay happens on its own, and it's not triggered externally. Okay, whereas random means you cannot predict the next decay. So I'm putting this there for your notes for future questions. I mean, in case you need it. Okay. Question 7 now. Star cluster P is twice as far from Earth as cluster Q. The intensity of light from a standard candle in P is IP. The intensity of light from the same type of standard candle in Q is IQ. Which of the following is equal to the ratio IP over IQ? So let's write it here. So IP over IQ. Okay, this would be, IP will be the luminosity over 4 pi, and then the distance from P squared. And then for Q, we will have the same luminosity since these are standard candles, over 4 pi dq squared. So 4 pi cancels, L cancels. So this is equal to dq squared over dp squared. But dp is, so dq squared over 4 dq squared. So 1/4. So the answer is A, because we are given that star P is twice as far from Earth as star cluster Q. Okay. 8. A student investigated the absorption of gamma radiation by lead. She placed a Geiger-Müller tube a few centimeters from a gamma source as shown. The corrected count rate without the lead was 240 counts per minute. Lead with a thickness of 2.5 millimeters absorbs 50% of gamma radiation. Which of the following could be the corrected count rate when lead with a thickness of 4 millimeters is used? Okay, I'm going to use a clean page for this. I didn't check the mark scheme. Maybe there is an easier way to do it, but this is the way I did it. So the count is 240 counts per minute. Okay, the thickness is 2.5 millimeters, block 50% of the radiation. So the formula is I equals I naught e to the minus mu x. I naught is the initial intensity of radiation, and I is whatever remains after. So if you have an absorption foil, okay, of thickness x, okay, and this absorption foil has some characteristic mu, which is a characteristic of the material. So if you have some intensity I naught, after it passes through this material, there is a new intensity I. And they are related through this formula that was introduced into Unit 5 via the Core Practical 16, I believe, which is about absorption of radiation. Okay, so you need to know this actually. So it's in the new spec. Okay, so if we do I over I naught equals to the e to the minus mu x, we can immediately say that, okay, we are told that that if the thickness is 2.5 millimeters, 50% remains. So we have 0.5 I naught over I naught is equal to e to the minus mu times 2.5. Okay, and if we rearrange, we can find that mu is equal to ln of 2 over, did I go too fast over this? Maybe I went through too fast. Let me take one more step. So e to the mu times 2.5 is 2, okay? Is that correct? So 1/2, yes, it's correct. So if we take the ln, we have mu times 2.5 is equal to ln of 2. So mu is ln of 2 over 2.5, or what's the answer? 0.28 millimeters to the minus 1. Okay, so for 4 millimeters, then, for 4 millimeters of material, I hope I make sense, by the way, we can use again I equals I over I naught is equal to e to the minus mu times x, and we plug in mu is equal to minus 2.28, x is 4, and we have millimeters over millimeters, so the exponent is a pure number. Okay, and if we do the calculation, we find 0.33. Okay, so I is 240, which is I naught, times 0.33, or 79.17, or 80 counts per minute. So once you know mu, this quantity over here, you can find how much radiation will pass through for any thickness you want, okay? And by the way, I named it C. This is actually I naught, okay? So up here, it makes more sense to write I naught. Okay, so the answer is B. Okay, this was a little bit tricky. Okay, question 9. A student finds the diagram shown on a website. He notices that the labels on the axis are different from those in his textbook. Okay, which row of the table gives the spectral class of each type of star? Okay, so let's start with M. Okay, so M is a cool dwarf star, right? Because remember that in the this is a Hertzsprung-Russell diagram, and in these diagrams, temperature increases to the left. Therefore, M here has the lowest temperature, whereas O has the highest temperature. Now, M is in the main sequence, so it's just a dwarf star in the main sequence. So So the correct answer is either B or D. Okay, now let's examine G. G is what kind of star? It's they mean this cluster up here. Okay, so this cluster up here are cool giant stars. Okay, so this corresponds to the row D pretty much of the table. And then let's read the other ones. We found the answer actually because B is wrong. So D is the correct answer, but let's go see why. If we move on to A, okay, A is a hot dwarf star because it refers to these stars over there. Okay, and then O is a hot giant star in the main sequence. Okay, so D is the correct option here. All right, 10 looks scary, but the answer is simple. Okay, a student used a heater to melt ice as shown. The heater was switched on for time t. The student measured the mass of water that dripped into the beaker. She used her result to calculate the specific latent heat of fusion of water L. Which of the following explains why the calculated value of L was less than the accepted value? Okay, let's see the options. The initial temperature of the ice was less than 0 degrees Celsius. No, that's not the case. B, the time recorded by the student was greater than t. That the time doesn't affect the measurement of the latent heat. C, some of the melted water did not drip into the beaker. Okay, but D says some energy was transferred to the ice from the surroundings, which is the correct answer. Okay. Right. So this was section A. So I have to admit that I think this was on the harder side of section. I mean, from the papers I've seen, I think this was a hard section A, but you let me know in the comments. And also, speaking about comments, guys, 85% of you are watching these videos, and thank you for that. But you don't subscribe; it doesn't cost anything. So please subscribe. So let's move on. Section B. Question 11, the spectrum of atomic hydrogen has 4 lines in the visible region as shown. Okay. By the way, I hope you guys are aware that you have spectral lines that are not in the visible spectrum. Okay, for most elements, actually all elements. Okay. The hydrogen spectrum for light from a nearby galaxy is analyzed. The 486 nanometer line is observed at a wavelength of 502 nanometers. Okay, calculate the magnitude of the velocity of the nearby galaxy relative to Earth. Okay, so this is a redshift, first of all, because lambda observed is larger than lambda lab. Okay, because we observe 508 nanometers, and in the lab we observe 486 nanometers. Okay, so delta lambda is delta lambda over lambda lab, it's always lambda lab in the denominator, by the way, is 508 minus 486, okay, over 486. So we subtract from the observed wavelength in the lab the observed wavelength from the galaxy. Okay, so this is 0.0453. So V over C is, and this is equal to Z, the Doppler factor. This is equal to Z, so V is 0.0453 times C, or 0.0453 times 3 times 10 to the 8. And this yields 1.36 times 10 to the 7th meters per second. Okay, question 12. A student pours 210 grams of a solution of dilute acid into a beaker. She adds 95 grams of a solution of dilute alkali. The initial temperature of both solutions is 18.2 degrees Celsius. The temperature of the mixture in the beaker increases to 27.5 degrees Celsius. Calculate the total energy change as the temperature increases, and they give you the specific heat capacity of each solution to be the same pretty much, and equal to 4,180 joules per kilogram per Kelvin. So this sounds scarier than it is actually, because they make it sound like a chemistry problem, but it's not. We simply need to use delta E, the change in energy, is equal to C times M times delta theta. And for M, we will plug in the combined mass of the two mixtures, which is 210 plus 95, right? Or 305 grams, okay? So let's plug in. So C is 4,180, then mass is 305, but we have to multiply by 10 to the minus 3 to convert to kilograms. And then delta theta is, I'm going to come down here, 27.5 minus 18.2. So the result is 11,856.6 joules, or about 1.2 times 10 to the 4 joules. Question 13. Many cars have airbags that fill with nitrogen gas if the car stops suddenly. An airbag contains 0.0875 kilograms of nitrogen gas at a temperature of 22 degrees Celsius. The pressure in the airbag is 103 kilopascals. Calculate the volume of the airbag, and they give you the mass of a nitrogen molecule, which is 4.67 times 10 to the negative 26 kilograms. Okay. Since we know the total mass of nitrogen gas, we can divide by the mass of one nitrogen molecule, right? So this is 0.0875 over 4.67 times 10 to the negative 26. And this will give us the total number of molecules, which is 1.87 times 10 to the 24. Okay? And now we can use the ideal gas law, right? So PV is NKT. We need the volume, so we solve for the volume. So volume is NKT over P, and I'm going to come down here. So this is 1.87 times 10 to the 24 molecules times K, which is 1.38 times 10 to the negative 23 times 295 over 103,000 pascals. Okay, and the answer is 0.074 cubic meters. Okay. Okay, moving on to question 14. Nuclear fission and nuclear fusion can release enormous amounts of energy. The graph shows how the binding energy per nucleon varies with nucleon number. Uranium U and hydrogen H are marked on the graph. Okay. Explain why the fission of a uranium nucleus emits much more energy than the fusion of two hydrogen nuclei. You do not need to carry out any calculations. Okay, so from the chart, this is the way I responded. Again, I haven't looked into the mark scheme, so please let me know if I messed up something. So, okay, from the chart, okay, uranium, let's just write U to save time. Uranium has a mass number of about 240. Okay, 240. If we assume it breaks into two nuclei of mass 120, then the available energy is about 240 times 1 MeV, or about 240 MeVs. How do we know that? Because if we look at the chart, that's uranium, okay? And the element 120 is somewhere here, say, okay? So this difference over here is 1 MeV, okay? For hydrogen, though, for hydrogen, assuming two hydrogens fuse, the available energy is simply 2 times, say, 4 MeVs or 8 MeVs from the chart. Okay, and let me go to the chart and explain. So this is hydrogen, okay? And if you fuse 2 of them, you're gonna come up here, okay? So the available energy is about, it's even less. I wrote 4, it's about 2 MeVs, okay? So actually we can erase this up and say 2 or about 4 MeVs from the chart. In both cases though, elements with a higher binding energy per nucleon are produced, with a higher binding energy per nucleon than their parents, than their parents are produced. Okay. B, nuclear fusion occurs in the course of main sequence stars. Explain the conditions that bring about and maintain fusion in a main sequence star. This is a 6-mark problem, long writing, so you should provide about 6 points. Let's start with the first. There must be a very high temperature in the core. Okay, this gives nuclei a high kinetic energy. High kinetic energy allows protons to get close enough to fuse. High kinetic energy to get close enough to fuse. High kinetic energy is needed to overcome the Coulomb barrier between the protons. I mean the repulsion, right? Because they repulse each other. There must also be a very high density or high pressure in the core. Okay, this gives a high collision rate, so fusion can be maintained. Right, and this is, I believe, a complete answer. I mean, I think we covered everything that needs to be covered. So let's move on to question 15. A simple pendulum has a length of 0.65 meters as shown. The sphere is displaced and then released. Show that the period of oscillation of the pendulum is about 1.6 seconds. Okay, for this one, we can simply plug in the formula. So 2 pi and then the square root of the length over g. So that's 2 pi and then the square root of 0.65 over 9.81, which is about 1.62 seconds or 1.6 seconds. Okay, The amplitude of the oscillation is 2.5 centimeters. Calculate the maximum kinetic energy of the sphere. Okay, so this takes a little bit of extra work. So the maximum speed in oscillations is equal to omega times the amplitude. So omega is 2 pi over the period times the amplitude. So if we plug in numbers, 2 pi over 1.62 times 0.025. So this is 0.097 meters per second, or about 0.1 meters per second. Okay. Now the kinetic energy max is 1/2 mv max squared, and they give us the mass. So we plug in 1/2 9.5 times 10 to the negative 2 times 0.097 squared, which yields 4.47 times 10 to the minus 4 joules, or about 4.5 times 10 to the negative 4 joules, which is the answer. Okay, this was question 15. It was a quick one. Okay, in 18th century England, salt was extracted on a large scale by heating salt water in open pans. The pans were heated by burning coal, as shown. Such a wonderful method. I mean, burning coal to get salt. I don't know, it sounds so inefficient. And for the record, in Cyprus, we have a large kind of lake, salty lake, that it's a salt lake pretty much, that dries during the summer. So back in the day, people extracted salt from there. They don't do it anymore, actually. So I don't know where we get salt from, to be honest. Anyway, so each pan was 24 meters long and 9.1 meters wide. The salt water was maintained at a temperature of 66 degrees Celsius. The graph shows how the latent heat of vaporization L of salt water varies with temperature theta. All right. The following information is given in historical records. The pan is filled with salt water to a depth of 0.5 meters. 6,000 kilograms of coal is burned to evaporate half the water in the pan. Evaluate the accuracy of this information given that the energy released by burning 1 kilogram of coal is 24 megajoules, and the density of salt water is 1,200 kilograms per cubic meter. Okay, let's find the volume of the salt water they evaporated. So that's length times width times height, right? So that's 24 meters times 9.1 meters times 0.5 for the depth. So 109.2 cubic meters. Okay, the mass then is equal to the density times the volume, or 1200 times 109.2, which yields 131,040 kilograms. Okay, the latent heat at 66 degrees Celsius is equal to, we can go back to the back of the paper. So 66 is over here, so 62, 66. Okay, so that's 66. So this is the value. Okay, so that's 2.34, pretty much. Okay, so 2.34, the units are megajoules per kilogram, megajoules times kilograms to minus 1. Okay, so to evaporate 131,040 kilograms, we need of salt water. Okay, we need energy equal to the mass times the latent heat. So 131,040 times, I divide by 2 in my notes. Why do I divide by 2? Let me see. because we need to evaporate half of that. This is what I say. To evaporate half the water in the pan. That's why I use 1/2. I'm sorry, for a moment I was confused. Okay, so to evaporate half of this, we divide by half, and then we multiply by the latent heat, so 234 times 10 to the 6. I'm sorry for the confusion. So that's 1.53 times 10 to the 11 joules. Now, 6,000 kilograms of coal yield 6,000 times 24 times 10 to the 6 joules when burned, or 1.44 times 10 to the 11 joules. So close, but not accurate. Okay, but to think that they burn coal to make salt is crazy. So anyway, let's move on to question number 17. The International Space Station is in a low Earth orbit. Astronauts on the ISS carry out experiments. One of the experiments is designed to detect dark matter. State what is meant by dark matter. So this is a type of mass, that interacts gravitationally but emits no electromagnetic radiation. Okay. B. The ISS moves in an approximately circular orbit and has a mean height of 420 kilometers above the surface of the Earth. Calculate the number of complete orbits of the Earth by the ISS in 1 day. And they give you the mass of the Earth, the radius of the Earth, and 1 day in seconds. So sigma F, the sum of all forces, is equal to the centripetal force, okay, that keeps this satellite in orbit. What's the force that keeps it in orbit? The gravitational force. So GMM over R squared is M omega squared R. M is the mass of the satellite and gets cancelled. So GM is omega is 2 pi over the period, and if we square it, we find 4 pi squared over t squared times r cubed. So t squared is 4 pi squared r cubed over gm. Okay, and if we plug in values, we find 4 pi squared times, now the radius is equal to the radius of the Earth, 6.4 times 10 to the 6 meters, plus the height, which is 420,000 meters above ground, okay, to the cube, over 6.67 times 10 to the negative 11 times 6 times 10 to the 24, and this ends up being 3.13 times 10 to the 7, and this is second squared because we are solving for t squared. So we have to take the square root to find t equal to 5593.9 seconds. Okay, now if we divide, so 86,400 seconds by this period, okay, we will find the number of rounds, the number of orbits, the number of times around the Earth. Okay, 93.9. So this yields 15.4. So about 15 times a day. So for our friends, the astronauts on the ISS, the sun, they see the sunset 15 times a day, which is crazy. So, all right. C, a student reads on a website that astronauts on the ISS experience weightlessness. The student states that astronauts on the ISS have no weight. Assess the validity of the student's statement. So let me do a demonstration for you. So at the height, at the height of the ISS, G, the gravitational constant, is G times m over r squared. So if you do the calculation using r equal to the radius of the Earth plus the height, you will find 8.6 newtons per kilogram. On the surface of the Earth, that's 9.81, so it's really close. So they do have weight, okay? So they do have weight, but they are in a continuous free fall, okay? But they do have weight, okay? So student is wrong. All right, moving on to question 18. Exoplanets are planets outside our solar system. 7 exoplanets orbit the star TRAPPIST-1. TRAPPIST-1 has a surface temperature of 2570 Kelvin and is described as a red dwarf star. A typical red dwarf has a radius approximately equal to 10% of the radius of the Sun. Deduce whether TRAPPIST-1 is a typical red dwarf star, and they give you the luminosity of TRAPPIST-1 and the radius of the Sun. So we have to solve for the radius pretty much using the Stefan-Boltzmann formula. So L is sigma times the surface area, which is 4 pi r squared times t to the fourth. So r squared is L over 4 pi sigma t to the fourth. So r is the square root, okay, of 2.13 times 10 to the 23rd over 4 pi times 5.67 times 10 to the negative 8 times 2570 to the fourth. Okay, so this is equal to 8.28 times 10 to the 7 meters. So if we divide that with the radius of the Sun, so r over the radius of the Sun, we will find 8.28 times 10 to the 7 over 6.96 times 10 to the 8, or 0.12, so about 12% the radius of the Sun. So the statement is correct. Statement is correct. Okay. Question 2. TRAPPIST-1 emits radiation with a peak at wavelength lambda max. Show that lambda max is about 1.1 times 10 to the negative 6 meters. We will use Wien's law. So lambda max times T is 2.898 times 10 to the negative 3 meters Kelvin. So lambda max is 2.898 times 10 to the negative 3 over 2570, so 1.13 times 10 to the negative 6 meters, which is about 1.1 times 10 to the negative 6 meters. Okay, 3. The visible spectrum has a range of wavelengths from 400 nanometers to 750 nanometers. Explain why TRAPPIST-1 can be described as a red star. So lambda max is, if we write it in nanometers, it's 1130, so 1130 nanometers, or IR. Okay, so most radiation is red. And let me show you the graph. So if we make the graph for this star, it will have a peak, say something like this. So that's 1100. So this will be 700, say. So most of the radiation will be in the red. Okay, so that's the idea. It will have less radiation in the blue region, for example. I mean, the blue region is over here. So that's say 400 nanometers. Okay, so that's the idea. B, one of the exoplanets is a rocky Earth-sized planet. Scientists think this planet has an atmosphere. The exoplanet has a radius that is 92% of the radius of the Earth. Calculate the value of the gravitational field strength at the surface of this exoplanet. And they give you the radius of Earth and the mass of the exoplanet. So the radius of this planet is going to be 0.92 the radius of the Earth, or 5.89 times 10 to the 6 meters. So G is again G m over r squared. So 6.67 times 10 to the negative 11 times 4.15 times 10 to the 24 over 5.81 times 10 to the 6 squared, which yields 7.98 newtons per coulomb, per kilogram. Sorry. So you can write 8 newtons per kilogram, or meters per second squared. It's equivalent. All right. Calculate the mean kinetic energy of gas molecules at the surface of the exoplanet, and they give you the mean surface temperature at 235 Kelvin. That's what, minus 40? That's not too bad. I mean, it's similar to what? Some areas in Alaska, Canada, even Illinois, sometimes it went down to minus 30 degrees Celsius, which is 240 Kelvin. So yeah, okay, not too bad. So 1/2 m times the average velocity squared of molecules is 3/2 kT, or 3/2 times 1.38 times 10 to the negative 23 times 235, right? So 4.86 times 10 to the negative 21 joules. Okay, question 3. Higher up in the atmosphere, the movement of charged particle causes a heating effect. Suggest why heating the upper atmosphere may cause the density of the atmosphere to decrease. So as the temperature increases, the kinetic energy of the molecules increase, as we saw, I mean, from the formula. So more molecules will escape by acquiring escape velocity, escape v. So the atmosphere, I'm sorry, becomes less dense. All right, moving on. Question 19. Polonium-214 is part of a naturally occurring decay chain. And it's also a famous poison used in spy movies, and not only. Okay, I shouldn't be saying these things, but yeah, I mean, look it up. So the nuclear equation shows the decay of polonium into lead by the emission of an alpha particle. Calculate the energy in MeVs released in this decay, and they give you the masses of these isotopes. So let's find the mass difference. So delta M, you always subtract the mass of the parent, minus the daughters, the decay product. So mass of polonium minus mass of lead minus mass of alpha. And if we do this, we find 8.41 times 10 to the negative 3 atomic mass units. Let's keep the atomic mass units, and let's jump into our guy Albert Einstein formula. So delta m c squared. So 8.41 times 10 to the negative 3. And this atomic mass units, one atomic mass unit is 1.66 times 10 to the negative 27 kilograms times 3 times 10 to the 8 meters per second squared yields 1.26 times 10 to the negative 12 joules. And if we divide by 1.6 times 10 to the negative 19, we will find this energy in EVs. So 7.85 times 10 to the 6 EVs, which is equal to 7.85 MeVs. B. Explain why the maximum energy of the alpha particle is less than the energy released in the decay. So due to momentum conservation, okay, the recoil nucleus must have some kinetic energy. Okay, so not all the energy goes. So not all delta E goes to the alpha. Okay. B. The lead-210 decays to bismuth by beta emission. Complete the nuclear equation for the decay of lead-210. Okay, so the beta particle has a mass number of 0, atomic number of -1. Therefore, bismuth has 83 protons, 83 minus 1, 82. And 210 is the mass number of bismuth. The beta decay does not change the mass number. Okay. 2. A cross section of a river is shown. Mud at the bottom of the river contains lead-210. The activity of the lead-210 in the mud can be used to determine the age of the mud. This method is only accurate when the activity of the lead is greater than 2.5% of the initial activity. A textbook states that this method is not accurate for mud more than 100 years old. Deduce whether the textbook is correct, and they give you the half-life. So from the half-life, we can calculate lambda, the decay constant. So lambda is ln of 2 over t1 half, or 0.031 years to the -1. And we can calculate how many years it will take to have at least 2.5% left. So by using A, the activity is equal to the initial activity e to the minus lambda t. We have done this already in this test, so I'm gonna probably skip to the final result, or maybe I can take a few steps. So minus lambda t is ln of A over A naught. So let me use a clean page. So t is -1 over lambda ln of A over A naught. So this is minus 32.17 times ln of 0.025, and this over here is 2.5%. So this means 2.5% of the initial activity left, and it will take 118.67 years to have 2.5% left. So in 100 years, so since 118.7 say years is larger than 100 years, the textbook is correct. And this is because if we have 2.5% left in 119 say years, then in 100 years we will have more than that. So it will be maybe 4%. Okay, so yeah, let's move on. Part C, radon-218 is also produced as part of this decay chain. Radon-218 is a radioactive gas that decays by emitting alpha particles. Explain why radon gas is a potential hazard. So the problem is that alphas are highly ionizing So especially if inhaled. So this is why it's dangerous. And also radon is heavy and sits at the bottom of buildings. Okay, and this is the reason why if it's inhaled, it's dangerous because, yeah, I mean, it's a gas just like air. It contains alpha particles. They can go into your lungs. And I know that in the US they check basements for radon because it sits on the bottom of buildings because it's a very heavy. I mean, it's 218, so the density is really higher than air. So it sits in the bottom of buildings. Okay. Question 20. The Inside Lander is a robot explorer designed to study the planet Mars. Again with Mars. Okay. Question A. The graph shows how the gravitational potential varies above the surface of Mars. I wonder if Elon Musk funds these boards. I mean, if he funds physics textbooks and stuff like that. I mean, if he does, that's cool. Please fund me as well. So I don't know, because Mars keeps coming up all over and over and over again in this test. So I wonder if there is a connection. So, all right, distance from center of Mars and then gravitational potential. I mean, I'm talking about this graph over here. I show that the mass of Mars is about 6.4 times 10 to the 23 kilograms. Okay, how are we going to do this? We can use values from the graph. Okay. So we can use V is equal to minus Gm over R. So M is minus V times R over G. So that's minus, if we took this value over, if we take this value, okay, minus 12. So let's use minus 12 times 10 to the 6. And then the distance here is 3.58 times 3.58 times 10 to the 6. And the values are joules per kilogram and meters. Okay. And then the gravitational constant in the denominator, 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared. Okay, so kilogram cancels, meter cancels, newtons per meter is a joule, so this cancels as well, and we arrive at the answer, which is 6.44 times 10 to the 23 kilograms, which to me appears to be about 10 times less than the mass of the Earth, because I think the mass of the Earth is 6 times 10 to the 24 kilograms. Okay. 2. In the final stage of landing, InSight moved from a height of 124 kilometers down to the surface of Mars. Determine the change in gravitational potential energy of InSight, and they give you the radius of Mars and the mass of InSight. So the change in gravitational potential energy is equal to the mass of the object times the change in potential, gravitational potential, which is different from gravitational potential energy. Okay, so this is equal to mass times minus Gm times 1 over the radius of mass of Mars minus 1 over the radius of Mars plus the height. Okay, I hope this makes sense. I took the Gm factor outside, the minus Gm factor, and then delta V is equal to the gravitational potential at the surface of Mars minus the gravitational potential at the height we start with. Okay, so if we plug in numbers, we find minus 6.67 times 10 to the negative 11, and then times 6.44 times 10 to the 23 times the mass of the object, which is 358, times 1 over 3.4 times 10 to the 6, minus, I'm going to come down here, 1 over 3.4 times 10 to the 6 plus 124,000. Okay, and this energy is 1.6 times 10 to the 8 joules. Okay, it's a large energy. Okay. 3. A parachute was used during the final stage of inside landing on Mars. Explain why a parachute was needed. You should not do any further calculation. So it introduces a drag force, pretty much. It introduces drag. Okay. So this means the terminal velocity reduces. The terminal velocity reduces. I mean, compared to not using a parachute, okay? So this reduces, so delta P, the change in momentum on impact, reduces, and less damage to, less damage to inside. Actually, you don't want to have less damage, you want no damage, right? These are multi-billion dollars expeditions. I mean, from the inception of designing one of these spacecrafts and launching them, the personnel, for highly trained personnel, you need engineers and stuff to program these things. Yeah, they cost a lot. So yeah, you don't want them to break. So, all right. And part B, if InSight had landed on Earth, a much smaller parachute could have been used. I'm sorry. Suggest why the parachute used to land on Mars needed to be much larger, and this is because okay, the atmosphere of Mars is much less dense than that of the Earth. And in fact, I believe the density of the Martian atmosphere is 1%, the density of the Earth's atmosphere, which is crazy. Anyway, I went over this a little bit fast because I have some other things to do today, and I hope this is useful. This is the most recent test. Soon I'm going to be uploading Unit 6 and hopefully 1, 2, 3 as well. And recently someone requested the mechanics paper. I'm going to look into it. No promises. I'm going to upload videos. Thank you for those of you who are subscribing. This helps the channel, but it doesn't help me yet. But hopefully this community will grow and people will find help. Yeah, something like that. See you in the next one, guys. Bye.